And now on BBC One, a little later than we'd planned, a year in the life of the Hubble Space Telescope with Patrick Moore.
Good evening. A few weeks ago, there was a total eclipse of the sun. Nothing ever was seen from here, but it was visible from South America. In Bolivia, Les Roberts took these pictures, showing how the landscape darkens as the moon's shadow sweeps toward the Earth. I was in Peru. Don Bash was in Chile and took this lovely picture just as the eclipse ended and had the diamond ring. And I must say, I think a total eclipse is the grandest sight in all nature. Unfortunately, we are not going to see one here until the 11th of August, 1999, when the track will cross Cornwall, and I promise you a special Sky at Night program about it then. But meanwhile, on to something very different. Everybody's heard of the Hubble Space Telescope, a great reflector with a 94-inch mirror launched into a path high above the atmosphere, where seeing conditions are perfect all the time. Unfortunately, it turned out to have a faulty mirror. Frankly, that was human error. But a brilliant repair mission has put it right, and now the Hubble telescope is every bit as good as had been originally hoped, and is sending back amazing results. And this, frankly, is going to be a kind of a picture show. And who better to join me than Professor Alec Boksenberg, Director of the Royal Observatories. Welcome back, Alec.
Hello.
I think you will agree that the Hubble telescope is a real triumph.
Well, I must say it is. When it first went up and we saw those pictures, to say that we were disappointed would be an understatement. But now it's been repaired. It's very stunningly good, and everybody's so thrilled.
So let's begin with something that hit the headlines a few months ago, the impact of Comet Shoemaker-Levy 9 on Jupiter. The comet was discovered as what's described as a squashed comet. It was going round Jupiter, and what had apparently happened was that it had been behind Jupiter and had been literally torn apart by the giant planet's gravitational pull. So it emerged rather like a string of pearls. And then it was found that it would actually impact the planet in July of this year, which it duly did. And we all waited with bated breath to see just what was going to happen. And the best views were obtained from the Hubble telescope. Look, for example, at this. There's a composite showing how the comet came in. That black spot on Jupiter is the shadow of the satellite Io. And here is a picture of the impact of fragment G on the lower left-hand side of Jupiter. It caused a tremendous disturbance in Jupiter's outer gas, more so than we expected. And this magnificent picture shows what really happened there. Remember, of course, Jupiter has a gaseous surface. But the impacts were very much greater in extent than anyone had predicted, and they were very obvious indeed, weren't they?
Oh, they were immensely so. Everybody who had a telescope was watching that. Several impacts, of course, occurred, and the one that you now referred to, which is impact G, near the edge of the limb there, that was one of the major ones. You can see the sort of circular geometry of the impact area. That's having an effect on the atmosphere like the sonic boom has on the Earth. And there's by the way, there's the D, which happened about a day earlier than G, right in the same picture. Now, this is a view as if you were looking over the atmosphere right on top of it. It's been sort of deprojected, and that's an astonishingly clear picture of one of the impacts. The other impacts, which occurred in sort of a sequence, were interesting to watch. Here's an image of Jupiter in a sort of Mercator's projection that is how it looked before any of the impacts, and then after everything happened, this is how it looked after in fact, the last impact. So those holes in the image are simply gaps in the pictures as they were put together to make them look the same in terms of the coverage. And as time went by, this is a few days later, you can see the development of these plumes and so on. There are east-west winds which gave shear to the structures, but the interesting thing is, as you can see here too in this final picture, the color looks roughly the same. So the chemical constitution of the material, which is basically the comet material, remained roughly the same, and it just dispersed in the winds, in the wind and weather structure of Jupiter.
Well, you can see a good deal from Earth. I mean, I had good views from my own observatory, but of course nothing like that, and Hubble's given us by far the best views. And fascinating to see what's going to happen when Jupiter comes back into view again, which it will do in a few weeks' time. But Hubble's main task lies far beyond our own particular solar system. For example, there's a remarkable exploding star called Nova Cygni, and there it is right in the middle of the picture. And that's produced a shell of material around it that the Hubble has viewed, and very interesting indeed.
Well, it's very fascinating. A nova is a star, it's a sort of degenerate star, dwarf white dwarf, in fact, at the end of its life, being rained upon by a companion star, and that produces quite a hot atmosphere, and in fact thermonuclear reactions occur, and this shell structure came from that. Now this is an image which Hubble saw before the repair, and it looks a little fuzzy. In fact, it's not terribly fuzzy because it's been computer enhanced, but nevertheless it's fuzzier than it would be with the current optics. But this shows how it was some months before the second time it was looked at, which is now, this image shown now, and that's after the repair. Now it is somewhat clearer, yes, but the actual change in the structure of this gaseous shell is very clear, and that is the first time anything like this has been seen.
I've been very impressed particularly by Hubble's pictures of that remarkable southern variable star, Eta Carinae.
Eta Carinae is a very, very peculiar object. It's flared up in the end of the 1830s to the 1840s. I think it was at its brightest in 1841, maybe the second brightest star in the sky. And it's been changing ever since. It's seen in the middle of this ground-based picture that we now have up, and it's somewhere in the center there, but this is quite a large-scale picture. If we home in a little more closely, it's in this image to the upper right there, but seen on the Hubble, there it is. It's astonishingly clear. What you can see is, in fact, there's an erupting system. Think of it being initially as spherical, but there's a collar near the star itself, at the center there, which is holding in the central part, pinching it, and you can see, therefore, two plumes coming out. The top one is advancing towards us, the bottom one's away from us. It's so very obvious in this stunningly good picture, isn't it?
It is indeed, because Eta Carinae is a very, very massive star, highly unstable, and could one day, I don't know when, go off as a supernova. We haven't had a supernova in our own galaxy for a long time, but in 1987 we did have one in a neighbouring galaxy, the Large Tower de Magellan.
Indeed, called the Supernova 1987A, the first in 1987 that was really seen. And it's, in fact, it was a visual eye object, even though it's in a neighbouring galaxy. There is the galaxy Large Magellanic Cloud before the supernova event. And then afterwards, just a couple of days or so afterwards, there it is. And it's a star in that same galaxy. Most of the stars there are just in the fuzz in the background. What happens in a supernova explosion is something like this. The gas cloud around the star expands rapidly after the core of the star has collapsed. And this is a very energetic process, of course. It gets so bright. And what happens then is it leaves behind a very dense sort of remnant star, a neutron star or a black hole. Now what Hubble could do was to see this expanding shell as it actually moved out. This could not be seen before. Mm. And on 3 occasions, observations were made like this, and you can see very clearly that it's growing in size. Now, this followed very well expectation from theory of how these things occurred. Another thing that we saw with Hubble Space Telescope was a very curious ring structure around the supernova. The yellow ring is part of the gas structure that was blown off before the supernova event occurred, and then was lit up much later by the flash of the supernova. And this is very important. It gave the possibility of getting a really accurate distance to that object, and indeed to the Large Magellanic Cloud. Here's a sort of another cartoon showing how this was done. By measuring the time between the real flash and the fluorescent light from that ring, gave that distance r. By measuring the angle A, which is easy to do from the ground, and having that value of r, easily we got the value of d, just using trigonometry. And that's 169,000 light years away.
So we're seeing something that actually happened 169,000 years ago. Hubble gave a splendid view of it. Well, still in the Large Magellanic Cloud, let's have a look at 30 Doradus, otherwise known as the Tarantula Nebula.
Well, this is a very important region that's very obvious in the Large Magellanic Cloud. It's a gaseous region lit up by stars which are forming, and there's a region in that system called the R136, which at one time, from ground-based images, seemed to be just a few stars, and if there were just a few, they were so massive that it was not really supportable with known theories. In fact, Hubble showed that it is made up of many thousands of stars. So in a sense, it's a mundane object now, but nevertheless, very interesting for theorists and also to understand how star clusters like this evolve.
Well, it's a great pity that the large cloud is too far south to be seen from here. We can't do that, but we can see the lovely constellation of Orion, which dominates the winter sky in the evenings. Look in the south, and there you will see it, the celestial hunter, with the lovely orange-red star Betelgeuse in the upper left corner, and the supergiant Rigel lower right, 60,000 sun power. And there are the three stars marking the hunter's belt. And below the belt, the misty sword containing the gaseous nebula M42, Messier 42. And that is a stellar nursery where new stars are being born.
New stars are indeed being born. We're only really seeing part of that nursery. What it is a really large gaseous structure which has a lot of molecules and dust, and what we're seeing is only a part which is lit up by stars formed near the sort of nearby edge of it. It's like seeing a cave lit up by a fire, whereas the rest of the mountain is not in view. And several images, of course, are obtained from the ground, very good ones. Here's a nice ground-based image, but the Hubble Space Telescope was able to focus in on that and look at the wonderful structure which is now very evident. And amongst all the gaseous structures that one sees there are very interesting regions like this where new stars are being formed. There's even sort of protoplanetary disks around them. There's one in silhouette. There's enough mass in that dark bit that's in silhouette against the bright background to make up several Earths around that central star. The way that stars generally are thought to have formed, and it's not a very difficult process, is that the gas which was originally there got pulled together by gravity and hot enough in the center to produce a thermonuclear furnace, basically hydrogen burning to helium initially, and as that got into a nice stable condition, the residual material around went into a sort of disk-like structure and eventually coalesced to form the planets we know so well.
Well, of course, the Orion Nebula is not very much more than 1,000 light years away, but Hubble looks very much further than that. Look at this magnificent picture of the spiral galaxy Messier 100 in the Virgo cluster. Now, Hubble has made a very accurate measurement of the distance and velocity of this galaxy. And that's turned out to be very important indeed, because it's rather upsetting many of our theories, particularly with what we call the Hubble constant. But I'm not going to say more about that now, because we're going to devote the whole of our next program to it. But suffice to say that M100 is about 51 million light years away. Much nearer home, what about our own particular galaxy, the Andromeda spiral? I can just see that with the naked eye. There's a ground-based picture of it. And here's a ground-based picture of the center of that galaxy. And it seems single. But Hubble's looked at it very carefully, and it's turned out that the nucleus appears to be double. So why is that? Can it be that M31 has actually swallowed up a smaller galaxy? It's possible. And galaxies do occur in clusters. Here's a picture of the Virgo cluster, again a ground-based one, and there are galaxies of all kinds there. And the main galaxy in that is M87, Messier 87, a giant elliptical system, and that ground-based picture shows a curious jet coming out of it. It's also a strong radio source. Radio astronomers call it Virgo A. And of course, the Virgo cluster is the nearest of the really big clusters of galaxies. Hubble's looked very closely at it.
Hubble's looked at several of the galaxies very closely, particularly M87. It's extremely clear. There's globular clusters, actually, that are spotted about there, and the jet is wonderfully clear. At the center is this very bright spot, which is unusual in galaxies of this kind. It's much brighter than it would be if it were made up of stars, actually. And this image is in a sort of broad band, taken in a broad band, but when looked at in the color of a particular species of gas, that is oxygen in this case, then you can see it looks like it's much more fuzzy, and it's got, in fact, when seen in close-up, a spiral structure in the center there that shows there's a sort of much more dynamic activity than one can tell from the normal images. By looking at the motions within this gaseous spiral, using, in fact, the spectrograph, one of the spectrographs on the Hubble Space Telescope, one can see through the Doppler effect what the relative motions are in that central region. That top one is coming towards us, and the bottom bit indicated there is going away from us. And from that relative motion and the distance to the center, it's possible to weigh how much material there is in the center there, which is about 3,000 million times the mass of the Sun. It's just got to be a black hole.
Well, I wonder, because there are plenty of active galaxies. What about NGC 1068? That's another.
It's another quite close by active galaxy. And this one is probably much more energetic than the one in M87, the central region of M87. But we can't see the core itself. It's obscured by a gas and dust ring around it, and the ring is sort of in our direction. What we can see is the beam coming out from the very bright luminous object which is surrounding the black hole, and it's that beam, just like a searchlight beam, that is so evident in that object. It's not possible to see the bulb of the searchlight, but that beam it shows there's an immense energy in there.
And what is all this telling us about the ways in which galaxies evolve?
Having sight of nearby clusters like the Virgo cluster tells us how these galaxies in general look at the current time. I mean, it's quite a long way from us, but it's the current time. And looking at earlier galaxies, which we can do with the Hubble Space Telescope, here's one which is at a redshift of 0.4, which puts it something like at half, as we see it, half the age of the universe. And what we see here are structures which are the same sorts of galaxies that we know, but in a rather different proportion, and also many more interactions between galaxies. That interacting pair is very clear. You can see the gas between them swirling about, actually one gaseous structure almost being shared between two galaxies. That happens rather frequently in these early clusters. There's also many more spiral structures compared with what we now see. So there's clearly an evolution that we are observing. Here's another cluster which is even further away, those very fuzzy images, redshift 2. That's at the very close to the maybe a 10% or 15% after of the age of the universe, after the Big Bang. And the central object, incidentally, is a quasar, which is the most extreme form of active galaxy. And that bunch there looks even more extreme than the nearer galaxy cluster that we saw from the Hubble Space Telescope. So we can trace out from very early times to the current times how these clusters have evolved. And it's clear that there's big changes.
A great deal has been learnt, too, from this gravitational lens effect.
Many of these galaxies that we see in these very distant clusters seem to be curiously elongated. And if you were to think they were simply spiral galaxies on their edge, then statistically there's too many of those. And in fact, what we can see rather clearly in many cases is that these are imaged by some intermediate object acting as a lens, but in this case a gravitational lens. In fact, it's like an astigmatic lens in most cases. And it pulls this out. So that's really a very much more distant galaxy seen in better focus, but also distorted by this intervening mass of material. And in rather extreme cases, whole clusters of galaxies do this to the background. Here's a very interesting example that Hubble Space Telescope showed. If we focus in on one sector there, you can see that those elongated galaxies make out a sort of circular structure. And from measuring those, the mass distribution of the lensing mass, which is a whole cluster of galaxies, can be mapped out, and that's really astonishingly important.
So we're looking right out into the depths of the universe in a way that only the Hubble telescope can do, where the seeing is perfect all the time. But in our own solar system, Hubble hasn't neglected that. And after all, most of our knowledge of the outer planets comes from one probe, Voyager 2, but Hubble is now having a look at them. And let's have a look, shall we, at what it's shown us about the green planet Uranus, discovered by Herschel way back in 1781. And there are 3 pictures of Uranus. From Earth, you can see very little on it, but you can see something there.
You can certainly see some structure in the atmosphere. In fact, that's a sequence of about 8 hours where something in the atmosphere is being, a bright spot is clearly moving. One can see that what the rotation period is. Of course, it's seen nearly pole on in this case, so one has to interpret that. But it's very it's new and very interesting.
The gaseous surface, of course, very little there, but it also has a system of rings, and Hubble's given splendid views of those.
The rings, incidentally, in this case, in this picture, it's not drawn in. It looks like it is. But that ring, Epsilon, that was not actually seen like that before. It was inferred because one could see from a background star, as the ring crossed, it dimmed the light of the star. We knew something was there, but not seen as clearly as this. It's really quite amazing to see that ring and also the inner ones, not really appreciated until we saw it with the Hubble Space Telescope.
And only Hubble can do it. And we've even got pictures back of the planet Pluto and its satellite Charon.
Yes, for a long time one didn't know that Pluto had a satellite, but from the ground one could in the end detect that, and other methods, speckle interferometry, one could indeed find that extra companion. But from the Hubble, not only the fact that it has a companion and so clearly seen here, has been seen, but also structure on Pluto itself. That is, brightenings and darkenings in the atmosphere and the surface, I should say more surface. And mostly it's methane, ice, and that shows that it has well, let's say the plutography can now be measured.
Well, we're getting results of all kinds. What next with Hubble?
Well, I think several things. There'll be many more measures of stellar distances and therefore galaxy distances, and this will yield a very good, accurate value of the Hubble constant. I think that might be in just 1 or 2 years. Many more measures of galaxies as they were in very early times, and their evolution will be made, and I'm sure that will be very important for most of the observations, most of the theoretical work done on formation of galaxies. Also, using the gravitational lensing effect, mass distributions, including dark matter, and how that reflects on the whole structure of the universe will be a very important outcome. But since it's going to last for so long, there'll be many things which I just can't guess at.
Well, undoubtedly, it's the most amazing telescope ever built, and it's now a complete and utter success. Alec, thank you very much.
Thank you.
And when we come back next month, we're going to talk about the Hubble constant, and again, using results of the Hubble Space Telescope. Meanwhile, if you want the latest information, then you can dial up our Sky at Night information line, 0891 800 330. And since our next programme doesn't go out until next January, I hope it's not too early to wish you all a very Merry Christmas. And so until 1995, good night.